Welcome to this class on electromagnetic induction. This is a very important topic, not only from the examination point of view, but also because of what it means to our modern world. You can imagine can you imagine what our lives would be like without all the machines and devices that we use, all of which use electricity? How do we use these machines? Because it is made possible because of the electricity that is generated. And how is this electricity generated? It is based on the principle that we are going to discuss today. Over 95% of the electricity in the world is generated using the principle of electromagnetic induction. And that is what we will be talking about today. Let us start our discussion by discussing magnetic flux. This is an important thing for you to understand electromagnetic induction. What is magnetic flux? What is magnetic flux? Well, magnetic flux is an indication of the lines of force passing through a coil. The lines of magnetic force passing through a coil. And let me explain what that means. If we were to take a bar magnet, then or we can swap the poles around. In high school, you have drawn the lines of force around a bar magnet. And how does it go? It goes from the North Pole to the South Pole in continuous loops like this. And then they come back here. Remember, while I'm not showing it that way, they are continuous lines which do not intersect with each other. And this is a diagram with which you're all familiar. If I were to place a coil here, remember this is a coil of a conducting wire. This is a coil. Now clearly the magnetic lines of force are passing through the coil. How many magnetic lines of force are passing through the coil? Well, it depends on many factors. It depends on how close is the magnet to the coil. Because the closer the magnet, the more the number of lines passing through the coil. That is one factor. The other is how strong is the magnet. The stronger the magnet, greater the number of lines of force passing through the coil. Another factor is how big is the coil. The bigger the area of the coil, the greater the number of magnetic lines of force passing through the coil. So there are three factors we have already discussed that decide the number of lines of force passing through the coil because of this magnet. All we have done is keep a magnet and it has a magnetic field around it, and we have kept a coil here. And we are trying to find out how many lines of force pass through the coil. It depends on the size of the coil. The bigger the coil, more the lines of force. It depends on how far the coil is from the magnet, and it depends on the strength of the magnet. The stronger the magnet, the greater the number of lines of force passing through the coil. Let me demonstrate the same thing here, and then we will continue our discussion. Here we have exactly the same thing that I used to explain this on the board. We have a coil and I have This is a coil made of copper wire. It's a very simple coil. And then I have a magnet. Now if I hold a magnet like this in my hand, then there are lines of force from the North Pole to the South Pole. This is a bar magnet, and you know exactly what the lines of force will look like. There are lines of force around the magnet. If I keep a coil near the magnet in this way, then some of the lines of force are passing through the coil because I hold it like this. I hold it close to the magnet. Now, how many lines of force are passing through the coil depends, like I said earlier, on how strong this magnet is. The stronger the magnet, the greater the lines of force passing through the coil. It depends on how close they are to each other. The closer they are, the greater the lines of force passing through the coil. It also depends on the area of the coil. The bigger the coil, the greater the area of the coil, the greater the number of lines of force passing through the coil. So these are three factors that we have already discussed. There is a fourth factor as well. It depends on the angle. If I were to turn the coil like this and place them like this, then the lines of force are not passing through the coil at all. Only when I turn the coil to face the magnet in this way, you can say that the lines of force are passing through the coil. If I were to turn it like this, then the lines of force are not passing. So the angle between the magnet and this coil also decides how many lines of force are passing through this coil. Now, why is this so important? Why should we worry about the magnetic lines of force passing through the coil? Well, electromagnetic induction is all about the magnetic lines of force passing through the coil. Now, we can say that in this picture, magnetic lines of force are passing through this coil because we have a bar magnet here. The total number of magnetic lines of force passing through this area of the coil can be called the magnetic flux. Magnetic flux is the total number of magnetic lines of force passing through this coil, and it depends on many factors. Let's look at the same concept illustrated pictorially. If you can look at the slides that I'm sharing with you. Once again, as I described earlier, we have a coil here. This is a coil which has been made up of a conducting material. This is our coil. And because of the bar magnet here, we have the lines of force from the bar magnet passing through the coil. Right? Now, there are multiple factors that decide how many lines of force are passing through it. You look at this illustration. There is a rectangular coil here, and that rectangular coil is this one. That is our rectangular coil. The parallel arrows B indicate the magnetic field. These are the magnetic lines of force. Now the question is to find out how many lines of force are passing through the coil. In the first picture, which is on the left side, you can see that the magnetic lines of force are perpendicular to the plane of the coil. The magnetic lines of force illustrated by B happen to be perpendicular to the plane of the coil. In that case, the total number of magnetic lines of force passing through the coil is simply given by B multiplied by A. B multiplied by A. That is because the area, the plane of the coil happens to be perpendicular to the magnetic field. What if the coil is tilted at an angle as shown in the picture on the right? In that case, the total number of magnetic lines passing through the coil are fewer in number. To draw it on the board, when the rectangular coil happens to be perpendicular to the magnetic field lines, B, and this is A. A is the area of the coil, and the plane of the coil is perpendicular to the magnetic field. Then the magnetic flux, which is indicated by the character phi, happens to be B into A. It is just a product because this indicates magnetic flux density. Magnetic flux density multiplied by the area gives you the total magnetic flux. This is the magnetic flux density. And this is the area of the coil. And when you multiply the two, you get the total magnetic flux. And this is simple because the plane of the coil is perpendicular to the magnetic field. What if the plane of the coil is not perpendicular to the magnetic field? So this is our magnetic field, and B, as usual, is our magnetic flux density, and we have a coil which is at an angle. So the coil is not perpendicular, but it is at an angle, and so let's say that the angle is theta. When the angle is theta, then you can see that the number of lines of force passing through the coil will not be simply equal to B into A, but it will be lower than that because you have tilted the coil. And in this situation, the magnetic flux through the coil happens to be B into A into cos theta. So this gives us the magnetic flux passing through the coil of area A because of the magnetic field which is given by B, and the coil happens to be at an angle theta with respect to the magnetic field, and that's what it means. So this is what will help us understand the next step in this discussion on electromagnetic induction. So now we have understood the concept of magnetic flux, which is the total number of magnetic field lines passing through a coil at any given time. Let's look at the next step in our discussion. Now, what is Faraday's law telling us? Faraday's law of induction says that an electromotive force is induced when there is a change in magnetic flux. An electromotive force is induced when there is a change in magnetic flux. And Faraday's law also tells us the magnitude of the electromotive force. What is electromotive force? It is the potential difference required to make a current flow through the conductor. So the electromotive force causes a current to flow through the conductor. Now, what is the magnitude of the electromotive force? It is given by the rate of change of magnetic flux. And that is the essence of Faraday's law of induction. So to go back to the board and look at our drawing once again. So we have a magnetic field uniform magnetic field illustrated by B. We had a coil which was at an angle theta with the magnetic field. The area is given by theta is the angle between plane of the coil B, and B is our magnetic field. So we calculated earlier that the total magnetic flux happens to be B A cos theta. Right? Faraday's law says that EMF induced in the coil. Now it is important to realize that there is a flux in the coil, and because there is a change in the flux, an EMF is induced in the coil. If there is no change in the magnetic flux, if there is no change in the magnetic field passing through the coil, then there is no EMF induced in the coil, and that is the meaning of this. If there is a change in the flux with respect to time, so as time passes, if the flux is changing for whatever reason, then an EMF is induced, then a current is induced in the coil. Another way to say it is, if the magnetic flux is not changing, then current is not induced in the coil. And this is Faraday's law of induction. Now there is one small additional aspect that we could discuss. If you could look at what I show you in the second camera, and then we will come back to the board. Now I told you that when I have a magnet and a coil, there are lines of force passing through the coil. Now an EMF is not induced in the coil right now because the magnetic flux is not changing. How could I make the magnetic flux change? I could do it by moving the magnet. I could do it by moving the coil, or I could do it by turning the coil. Any of these things will cause the magnetic flux in the coil to change, and there will be an induced EMF in the coil. Now the magnitude of the EMF will also depend on how many turns of the coil are there. In this case, I have 3 turns. You can see that there is 1 turn, 2 and 3 turns. This coil has only 3 turns. If I increase the number of turns of this coil, then the EMF induced by this moving magnet will increase. So the EMF depends not only on the rate of change of the magnetic flux, it also depends on the number of coils we have in this wire. So let us make one change to our equation to incorporate that aspect. This is the induced EMF when N is the number of turns of the coil. In our case, the small coil that I had only 3 turns. So N is the number of turns. N is the number of turns of the coil. Now, this is an extremely important concept, very simply illustrated in this equation. The induced EMF is equal to minus number of turns of the coil N multiplied by the rate of change of magnetic flux with respect to time. What does it mean? In simple terms, if we have a copper coil or a wire of some kind, and there is a moving magnet near the coil, then a current can be induced in that coil. Let us look at a simple demonstration of this. Now, I have here a magnet and a copper coil. Now, how do we detect whether there is an induced EMF in the coil? Well, we have simply connected a bulb here, and this bulb, if it glows, tells us that there is an induced EMF or an induced current in the coil. Now, this bar magnet has created a magnetic field all around it, and some of the lines of force are passing through the coil. But nothing is happening. The bulb is not glowing because d phi by dt is not a positive number or a negative number. It's 0. d phi by dt indicates the rate of change of magnetic flux with respect to time. And at the moment, because the magnet is not moving, because the coil is not moving, d phi by dt is 0. So there is no induced EMF. But what happens when I move the magnet? When I move the magnetic lines of force inside the coil change. This causes d phi by dt to be a non-zero value. D phi by dt now has a non-zero value because the magnetic flux is changing with respect to time. So as long as the magnet is moving, there is an induced EMF and a current in the coil, and you can see that the bulb is glowing. The other thing we did was, what happens if you increase the number of coils? Well, we can increase the number of coils to 3, and you can see that the bulb glows brighter. And why? Because there are 3 times as many coils now. I showed you that there are multiple factors that affect the strength of the EMF. One is, how strong is this magnet? Is it a strong magnet or a weak magnet? The second one is, how big is the coil? Now we can make the coils bigger or smaller. And you can see that the EMF induced is lower when the coil is smaller and much higher when the coils are bigger, because there are more lines of force passing through the coil. So there are multiple factors that determine the strength or the magnitude of the induced EMF. And this can be easily generated or easily demonstrated in a lab. Let us quickly see one demonstration of this. Once again, turn your attention to what I have here. I have here a copper wire. Now this is our coil, and I have a magnet in my hand which will create a magnetic flux inside the copper wire. Now we have connected a bulb to the copper wire. The bulb is not glowing because the magnetic flux inside the wire is not changing. The bulb can glow only if the magnetic flux in the copper wire starts to change. And how do we change the magnetic flux in the copper wire? By either moving the coil or moving the magnet inside. So once I move the magnet inside, you can see that the bulb begins to glow. You saw the bulb glowing. And the bulb glows only when the magnet inside the coil moves. And the moving magnet causes a changing magnetic flux in the conductor here, the coil, and induces a current in the coil. When it is not moving, there is no current flowing through the wire. So this is a very simple illustration of electromagnetic induction. This is the principle on which most of the electricity in our world is generated, because there is a changing magnetic flux inside a coil of wire. Uh, Another simple illustration of this could be in this simulation. We have a magnet, we have a copper coil, it's connected to a light bulb which is not glowing. Now, this is the magnetic field created by the magnet. But that magnetic field is not changing with respect to time, so the bulb is not glowing. When we make this magnet move, then it will create a changing magnetic flux inside the wire and therefore induce a current in the wire. And how do we move the magnet? Well, we can open the tap. This is an illustration of how a hydroelectric power plant would work. Flowing water from a dam will cause the turbine to rotate. The turbine is attached to a generator which has a moving magnet. The moving magnet creates a moving magnetic flux inside the copper coil and induces a current in the copper coil. When water flows faster, there is a greater induced current. When water slows down, the induced current is lower. When the water is shut off, there is no induced current because the magnetic flux is not changing. So this again is a simple illustration of what we studied today. Well, we have come to the end of this discussion. As usual, we will be sharing with you several practice papers. There are assessments, formative assessments at the end of every discussion. There are summative assessments at the end of every unit. There are board level practice papers as well as practice papers for competitive exams, all of which will be given to you. Of course, we will give the answer keys also to you, but I would encourage you to try solving these questions yourselves before referring to the answers. Here is one sample paper that I will show you, and all of these will be uploaded to the portal after this class. So the summary notes and the practice papers will all be uploaded and made available to you after this class. Kindly use them for your practice. I hope this was a useful session. I will see you in the next class. Thanks for watching.